So really the kind of big news at the moment is the next generation of 360, with the main difference being these fabulous new Pistonik drive units.
Yep.
So I presume in your relentless pursuit of reducing distortion, the drive unit was a natural thing to kind of look at. So where did the existing one come from, and why have you got the new one?
So, and the existing unit, well, this is the base unit here. We've also dealt with the upper base, but just for the size of the table and what have
Yeah,
you,
yeah.
we've just got the
Sure.
base unit shown
Okay.
here. The original units were really, really good units. Don't
Hmm.
get me wrong; they were absolutely the best that we could find
You
at the
find that
time.
time.
Um, and they met all of the goals that we really wanted. We wanted a high base output. We wanted a decent linear range. We wanted it to behave well, and
That's it.
the units absolutely did. And as I spoke about before, they're hard diaphragm, so they push resonance out of band. They ticked all the boxes at the time, but we're always looking where we can reduce distortion.
Which I think must be one of the great things for you as an acoustic engineer working within Linn. You know, you can have the time and the resources to be able to look at a specific aspect of a product and actually really drill down into the
Yeah,
minutiae of that in order to try and optimize it. It's
yeah,
a bit like there was discussion at the launch about F1, and it's a little bit of that, isn't it? You're just putting a lot of resources in, getting incremental achievements everywhere
it
along the line.
is. Well, also whether they're incremental are absolutely huge, and
Yeah.
one of those in this case, it really is
It
quite
really is,
huge.
yeah. And
Um,
certainly having heard the comparison yesterday, the differences are dramatic. Differences are really dramatic.
so really, and it was about it's not about the fact that we didn't kind of know those forms of distortion were there, but it's about getting yourself in the right position to do a decent job.
Mhm.
So probably about 6 years ago, we bought in some pretty high power finite element modeling
Mhm.
software, and bought in some simulation engineers, the
Yeah.
expertise to actually use it. So that's influenced a number of, I mean, it influenced this form of the cabinet. It influenced the heat dissipation. You know, we look at, we apply simulation to so many more things now. And as our expertise in simulation grew, we realized, well, there's probably more we can do with the drive unit
Mhm.
than we're currently being
Yeah.
supplied with. But that's also partly down to our new, not exactly unique, but reasonably rare situation of designing the speaker as a complete system with all the amplification.
Mhm.
So a traditional bass unit or drive unit that we buy from an OEM supplier, and they're amongst the best OEM suppliers of drive units in the world,
Yeah, it's a
they're,
serious bit of kit.
that's it. They're designing something. They don't know exactly where it's going to go. They're designing a unit that's going to be used by a lot of different customers, essentially. So you don't know the acoustic environment. You don't know the volume of the cabinet, whether it's ported, whether it's not. You don't know these things. You don't know the power of the amplifier that's going to drive it. So you build it very much with a lot of safety net.
Yeah, absolutely.
So of its total excursion range, how much this diaphragm can actually move, half of that will be what is described in industry terms as linear, and the rest is just there to try and stop it breaking itself. So before it starts rattling off its end
Yeah,
stops,
absolutely.
the suspension
Yeah,
stiffens up and it puts the brakes on,
yeah,
basically.
yeah.
Um, because we know everything about the environment our drive unit is going to
Of
operate
course, yeah.
in,
You've got a controlled environment, haven't you?
we were like, well, surely
You're predictable.
we can have more of that range as being linear. Um, so that was kind of the motivation for it. When we started then looking more deeply at what drive units do, we realized that the industry definition of linear wasn't quite our definition of linear as
Right.
well.
You gave some fairly interesting statistics yesterday on
Yeah,
that.
indeed,
Yes.
indeed. So linearity, it's worth very briefly explaining. And
So what is linearity? What goes in comes out?
broadly, yeah, but it's scalability as well. So a power amplifier is a really good example of it.
Mhm.
It's really easy to understand, and everyone would expect their amplifier to be a linear
Yeah.
thing. So if I'm playing at volume 10, I'm expecting it to be flat on its output with a certain level of distortion. If I turn it up to volume 60, the only thing I want to change is that volume, the output level. The distortion level should remain the same, and the bandwidth should remain
Yeah.
the same. Linearity.
Mhm.
Loudspeakers don't really do, or
Yeah,
drive
got it.
units don't
Yeah.
really do that. So the industry accepted linearity range for the force factor, so the strength of the motor,
Mhm.
is it's defined by when the harmonic distortion has increased by 10%. which when you actually do the math through is basically as long as it's within 18% of the force at rest.
Which sounds not exactly very accurate.
No. As I say, I mean, our electronics engineers laugh when I talk about loudspeaker linearity because this is not linearity.
Minutiae and you're in.
So we kind of figured we've got to be able to do better.
Absolutely.
There must be a way of achieving actual flat linearity for a much, much wider range. And that's what we went after. And that's why these two units look so different.
Yeah. So what are the elements then of a drive unit? How does a drive unit work?
Right. How long have we got?
Not that long, Phil.
So probably the most important part of your drive unit is the motor down at the bottom here.
Right.
So the motor works, you have a magnet, in this case, a neodymium ring, in this case, a big old ferrite ring, that's connected to bits of steel that transfer the magnetism to a magnet gap. Yeah. And that's what the coil operates in. Yeah. So your magnet gap is your permanent magnet. Yeah. That's a static magnetic field. And the coil inside it, when you apply a current to that coil, it turns into an electromagnet. So it produces its own varying magnetism.
Which is depending on the musical signal which comes in.
Yeah, so that interacts with the static field in much the same way that if you put two permanent magnets, you can push one about or pull it or whatever. So that's the fundamentals of how the motor system works. You're using that motor to drive the diaphragm, which pushes the air.
Okay. So in terms of the actual pieces that we're talking about, you've effectively got your permanent magnet around the outside. Your voice coil sits in the throat of
in a gap
somewhere in there, which wraps around the back of the actual diaphragm. And then when you put a current through it, it's attracted or these are too heavy for this.
I know.
These are attracted or repelled proportional to the musical signal that is delivered to it, really.
Yeah. So essentially,
wish I picked up the smaller one.
Your coil is on a former which connects to the actual cone, and making sure that as the cone drives in and out, that it stays central within that magnet gap and it stays where it should be. You've got the visible suspension element, which is your surround, and then you'll have a plurality, often just one, but maybe more than one of these suspension elements.
I don't think many people in the industry use the twins either, but
not many do, but we've got a very long travel. We've got to keep it centered.
Yeah, okay.
So there are two basic forms of motor as well. So we've got the basics of how a motor works, but essentially there's underhung or overhung. Traditionally, base units are overhung design, so you have a long coil in a short gap. So you have
a long coil in a short.
So you have a big, strong flux there, and the coil moves about. And in theory, you've always got the same amount of coil in that gap. It's subject to stray field. Outside of that gap, the field above and below will probably be different. So as the coil moves, you see the force that the coil is able to generate, that changes. And that's why the linearity is not a flat, straight line. The other approach is an underhung approach, where you have a short coil in a long gap. Now, as long as that coil doesn't move out of the gap, and
it should be more consistent,
got a constant flux in that gap, you end up with this flat line linear response. It's very, very unusual to see that in a woofer. It's normally reserved for tweeters because it's far easier over those kind of distances to make something that's not going to cause rattles, buzzes, and awful noise. But that is fundamentally why on Pistonik you see this much, much deeper motor structure, because this is almost all the gap. This is where the coil is moving within. So that gives us...
So you've effectively got a fairly large voice coil and a fairly large motor.
The voice coil is pretty short.
Okay.
It's not desperately long. It's about 8 millimeters in height, I think. It's 4 layers, so there's plenty of layers in there. There's plenty of windings to pick up that flux.
So you've used depth rather than length to give you the generator.
Okay. And it just means that you can use as much of the height of the gap as you can and stay within it. So obviously that gives Pistonik its really linear behavior.
So Pistonik's what you're calling the basically...
Pistonik is the motor.
The new motor unit, okay.
So that then feeds into, obviously is driving the voice coil, which is supported by the suspension. Now, suspension is another area in loudspeaker design where linearity historically has not been that great. And again, linearity is like the brakes on the car. That's the thing, that it's the returning force against which the motor is pushing.
Okay.
So from a typical OEM supplier, they want those brakes to come on reasonably early so the thing
So
doesn't
it doesn't
tear itself
yeah,
apart.
absolutely.
But as I said, we know exactly where the thing should be applying its brakes, so we can design this suspension system to be.
And I guess you can put some limiting within the drive, within the power amplifier modules.
We've no, yes and no. We could. We've
But you
chosen
haven't.
not to.
Okay.
What we've done is design the drive units to be able to cope with more than the amplifier can give.
Okay, yeah.
So it's always going to be
It's all
linear. It's
within
always going to be
operating parameters.
behaved.
Yeah.
Now, to be fair, you will know, having worked in hi-fi for many years, that whatever your best intention, someone will find a track that exceeds that.
Yeah.
So the suspension system in this does apply the brakes eventually.
Absolutely.
But the idea is to have a suspension system that is the mirror image in terms of stiffness. If you've got a force curve, then it will go, versus displacement along the bottom. It'll be nice and flat and then drop off at the extremes quite quickly. The suspension stiffness will mirror that perfectly, is really what you want. And that's what we've designed in here. I still remember my simulation engineer when we designed the first motor structure, trying to design the suspension. He was like, we've got this motor structure, and he's like, oh, it's a Ferrari. We've designed this Ferrari, and he couldn't get the suspension right, and it's got no brakes, which was disastrous.
Right, okay,
But that was it's been a very long process doing this. We were starting from a blank canvas. If we ground up development,
which is a great situation as an
it
engineer.
is. It's wonderful from that point of view, but the time involved in that is pretty huge. So then the final element on the drive unit is essentially the diaphragm, the bit that actually pushes the air.
So the material, that's aluminium?
Aluminium again. Lots of manufacturers use exotic materials in there, and we have. We started with a Brilliant. We've now got a carbon dome. We've got a carbon mid-range. It's useful for those. For these, the bandwidth is such that it's below where aluminium is going to break up anyway. So
So you really just want something that's light, rigid, and breaks up out with the audible operating range.
Even beyond that, we could have gone exotic and charged more for it, but it didn't need to be. There's many benefits with aluminium. It's ubiquitous. You can get it anywhere. It's easy to process. It's the finishing is of a high quality and easy to achieve. So there's many supply benefits to you.
And it's aesthetically pleasing, and the
It's
loudspeakers,
aesthetically
it
pleasing,
looks great.
and it does the job that we need it to. But with that said, we have done a little bit more. So we will always try and use engineering to improve things where we can. You'll notice one of the big aesthetic differences is that we have this inverted roll surround on our drive unit as opposed to the thing that you normally see out front. That's given us freedom to attach that surround where we choose to attach it to the cone. Now, this brings us benefit if you actually look at the vibration analysis of cone. If you appropriately connect to it with your termination points, you can actually calm down some of the resonance.
Okay.
So by judiciously fixing this around onto the rear of the cone, we've pushed the first breakup mode ever so slightly higher, like 40 hertz, not a lot. But we've calmed down the height of that resonance peak by about 18 dB. So even though it's out of band, it will notionally still be in the crossover range at some point. However quickly your crossovers turning the drive unit off. So pulling down a big spike by 18 dB is again huge. It's audible and it cleans things up. Don't add noise, add nothing. So if we can do that, we'll do that. So yeah, rather than just spending money, we applied engineering nous to solving the problem that we see there. So yeah, we've done everything that we can in this. I've spoken about how the motor works, how the suspension works, how the cone works. It's still very easy once you've done all of that. That would work perfectly in a vacuum. In reality, it's got to fight with air. So there's lots of places inside this drive unit where air wants to get trapped. So behind this dust cap where we're attached to the voice coil, you've got a pretty big volume of air between that and the motor.
So you really want to lose that because it's pressurizing.
We need to get
it's resisting the movement.
It's going to turn into a big spring to start with. So we need to be getting rid of it. So we've got ventilation all over this thing. There's ventilation laser cut into the bottom side of the cone. There's 3 rows of ventilation in the voice coil. We have a big, very flared port in the back of this to allow air to pass through there. And also at the bottom of the magnet gap, we've got these 8 holes in the bottom of the magnet gap as well. So that's really to allow clean air passage and silent air passage as well. And these in the bottom of the magnet gap, surprisingly important. We've spoken about quite a thick coil, 4-layer, moving up and down through essentially
moving a fair amount of
almost like a 40mm or bigger than 40mm, about 45mm gap. If you're plunging that down, you can imagine it's a bit like a piston in the car. It's gonna, the air's got to get round it somehow, so it ends up whistling. You can actually, on some units that I've heard over the years, you can hear it whistling past the coil. So all of these ventilation points are really, really important for an air compression point of view, but they also help immensely with cooling the coil. You're constantly pumping fresh air in and out of the system.
I suppose it's something you don't really think about, but yeah, a loudspeaker's a mechanical device, so it's moving, so it's generating heat, and I guess with heat, your performance changes.
The coil, absolutely. If you warm it, the coil is essentially copper. If you heat copper up, its resistance increases. So you change the behavior of the electrical side of the thing. You've made it more difficult to drive by the amplifier. It's all problematic. So keeping that at a nice stable temperature, really important. Giving the air that you're compressing or rarefying somewhere to go in a silent manner is really important. And the other thing that we needed to address quite strongly was it revolves around the electrical behavior or electromagnetic behavior of the motor system, is making sure that there's something called eddy currents. I spoke to you briefly about eddy currents yesterday, the man that I would love to employ.
Absolutely. Mr. A.
So as the coil, which is an electromagnet, is moving around within that the steel of the motor system, it wants to produce these things called eddy currents within the steel, and they would be contrary to the fixed flux that we want the motor system to sit at. That causes what we describe in the industry as reluctance, or is easier described as magnetic drag. You're weakening the motor as you pass signal through the coil. So the whole system wants to move a bit more slowly. It's almost like you filled the gap with magnetic soup. It's struggling to move through it. So to really tackle that, there's a couple of things that we've done. One is to guarantee that as much of the magnetism from this neodymium in the middle is going into the steel. So there's very little stray field. It's an immensely powerful, this tiny bit of magnet is far stronger than this big ferrite magnet here. We want to keep all of that flux in this steel. What that guarantees is that steel is fully saturated. If it's fully saturated with magnetism,
it doesn't gather.
It's going to pick up far less from the electromagnet of the coil. The other thing, and you're probably aware of this from other manufacturers, they talk about a copper sleeve that they put over part of the motor structure. We do have a copper sleeve in here. It's probably the longest copper sleeve I've seen in the industry because it's the full height of the gap, and that runs down the center pole. So the bit that sits inside the voice coil, that's a full copper sleeve. The copper sleeve, if people know anything about transformers, it's like shorting one side of the transformer. So basically the steel can still pick up eddy currents. The moment that turns into a current, it sees the copper and goes, oh lovely, I'll go that way. And it jumps out the steel and it's no longer a problem. So yeah, we've treated the electromechanical side, we've treated the acoustic compression side, and we've treated the thermal compression side. And it's one of those fun things when you actually go through the design of something and you start really looking in detail into things, is that, you know, all of these vents that I've shown you are solving more than one problem. Almost everything in here is doing more than one job. You can't just design it to do one thing. You've got to think of all the other impacts that it might have. So yeah, it was probably about a year and a half, I guess, of simulation work to get to the basic design.
It's a lot of work,
The remaining year and a half of development has really been getting it made.
Working out how to manufacture it, and I'm sure you gave your manufacturing partners a lot of headaches along the way.
We did, but I think they enjoyed it. If you find a good partner who's willing to learn, you know, if they want to improve as well, then you end up with a partnership that's really going to work and will stand the test of time. We found a partner just like that. They're perfect for us. They're the right size, the right scale. They want to do bespoke. They don't want to base off the platform. They want to do, let's just do it new every time. Let's make it right. But the standard manufacturing process for a drive unit is pretty straightforward. You have essentially one jig, you drop it into the motor, which is mounted on the basket, and everything gets built off that, and you sort of slide it down, you glue it, you move to the next one, you move up. We tried that on these, and the first ones were pretty disastrous. We got nowhere near the travel. It started making horrible noises and whatnot. So there was an awful lot of work involved with refining that manufacturing process. So instead of the one jig approach, we've now got 5, 6 different jigs that we use for building this up. And essentially what you're doing is making sure everything sits at exactly the right position, perfectly perpendicular to the coil and perfectly centered within the system. So everything is absolutely plumb and true, even to the point that we're holding the cone in its ideal position when it's bonded, because it wants to sag. It's on a set of suspension systems, and we live in a world with gravity. So even holding that and stopping the, I mean, it would only want to move by probably 1/3 of a millimeter, but we don't want that inaccuracy in our design. So it's jigged to, I don't want to use the term that I normally use. It's very well jigged.
Yes.
But it guarantees that the thing is built consistently and repeatably and reliably. The nub of it is, it's just fantastically lower distortion than what we had before. Any asymmetry in the motor force or the suspension typically results in a bunch of second order harmonic distortion. Any non-linearity in its behavior typically results in increase in third harmonic distortion. Because we've fixed both, we're almost perfectly symmetrical and very linear throughout that range. All of that distortion has dropped away. So harmonic distortion is way, way lower. But intermod distortion is ridiculously lower. So intermodulation distortion is when you've got a big signal and a small signal on top. So typically a low frequency tone and a mid frequency tone both being produced together. The low frequency tone is obviously pushing the drive unit quite a lot, and the mid frequency's got a wave about on top of that. The low frequency tone is always pushing the diaphragm on a conventional unit out of its linear range. So then when you're trying to do this high frequency tone on top,
It's quite difficult to do that.
well, it's not in the linear range of the unit. It's going to be full of distortion. With this, with the huge linear stroke, and we believe this is truly the widest and truly linear stroke in the industry for a low frequency unit. It just drives intermod distortion through the floor. And that's kind of what you heard yesterday. You mentioned that it's, you kind of chins on the floor. And we liken this in design to organic. It's a similar level of distortion reduction that we've achieved with the design of this unit to what we achieved with organic. So if you consider within a hi-fi chain, at any point, if you reduce noise by X number of dB, that's what you hear at the end. So it's just another place in the chain where we've taken out another 10, 15,
And you
20
just let that
dB.
with a cleaner, more accurate signal, and it just, I mean, it just sounded more realistic. It
Well, it
was
does.
easier to listen to yesterday. There was some quite dense tracks used in the demonstrations, and you could just sort through it with really any effort. It
Well,
just
yeah.
became much easier
Yeah,
to listen
the
to.
fun thing for me is that most people go, "Well, you've just done the bass unit." So, I mean, I like a bit of harmonic distortion on my bass, makes it sound big and warm and cuddly. And you're like, well, actually, we've not just done the bass. I often talk about the halfway split in music. So for classical music, 350 hertz is your halfway point. Half of your
50%
energy is
of
below,
it,
50% above. And that's for classical music that's got no bass, let's face fact. So you compare that to modern music, there's even more below 350. This unit, the bass unit goes up to 660. So we're dealing with about 70% of the bandwidth of music with these drive units down here. So everyone goes in listening for, I'm going to listen to the bass and see if it's improved, but it's vocals. It's everything. It's all.
It was an opera piece yesterday, and it was a female soprano. And just the clarity from the vocal and the emotion in the vocal came out as well.
Well, the separation, all of a sudden on that piece, you can hear the reverb from the cellos, and you're like, it was just lost before. You didn't know it was there. So yeah, I mean, the improvement in clarity is just insane with with these units. Obviously, I've been waving around the the lower bass here. The upper bass is essentially a scaled down version. All the technology in there is the same. It's weird compared.
Yeah, quite great. Okay. That was really comprehensive, Phil. Thanks a lot for that. Great stuff.
My
Cheers.
pleasure.